Schmidt does it. Maybe. I don't know. I should ask him. And then, of course, we have that the polynomial is continuous, and then the composite rule for limits. I need to get to the next thing, guys. I'm sorry. So maybe we'll come back and talk a little bit more about the deeper theorems of the calculus next time. But I should spend at least a few minutes today, since I am collecting your homework Thursday, and there is a question in your homework problem about this. So let's talk about it. Landau's growth notation, right? So this course, this has to be in this course because I think this course can substitute for like Math 250. And there's a reason this has to be here for the sake of, I think, computer science or something. And this is just good for us to talk about anyway. But so we'll start talking about it today. We'll talk more about it next time a little bit. But I want to make sure I talk about it enough today that you can do the homework, which I don't think is hard. All right. Let f and g be non-negative functions on some unbounded subset of positive real numbers. Then we write f of x is OG of x. So big O is read big O of g of x as x go to infinity. If there exists an m greater than 0 and an x naught, all right, such that the absolute value of f of x is larger than m times the absolute value of g of x for all x beyond x naught, right? So basically, eventually, you can bound your function by some scalar multiple of g. This is the idea of big order g, all right? So let's see if we have an example here. Example 9.72. So we have, all right, f of x is 3x cubed minus 2x squared plus 7. I'm going to argue that this is order x cubed. All right. Suppose x is greater than or equal to 1. Oh, I need my laser. Blue lasers are expensive. Nothing but the best for you guys. Let's see here. So we have this triangle inequality gives me that. But then the triangle, absolute value eats the minuses, of course. And we have this. And by the way, if x is greater than or equal to 1, then certainly x cubed is bigger than x squared, and it's bigger than 1. So I just make there's x cubes everywhere, right? Because we've got bigger than or equal to, which means 12x cubed bounds this guy above. So the absolute value of f of x is bigger than 13 times the absolute value of x cubed, which proves then that 3x cubed minus 2x squared plus 7 is order x cubed. Right? It's kind of a fancy way of saying, hey, this is the biggest thing in this expression, right? This is the dominant term as x goes to infinity. You can see why this is important to computer science in the study of algorithmics, right? If you want to understand how much time it takes for some kind of algorithm, then if you can come up with like a formula for the algorithm in terms of the number of steps n, whatever dominant thing in your formula is going to kind of inform how long that takes. So that's why big O is kind of important. Now here, this is a reciprocal, and I'm going to argue that it's order 1 over x squared. So if x is greater than or equal to 1, why is this true? What have I done? How can we make a fraction smaller? What do we do? What do we need to do to its denominator? If I make the denominator smaller, that makes the fraction bigger. It's reversed, right? If I make the denominator bigger, it makes the fraction smaller. So here I've gone from a larger denominator to a smaller denominator because x is greater than or equal to 1, right? So I'm no longer adding this positive term. I'm just looking at the smaller term x squared. And that's why we have this bound. And as such, the absolute value of f of x is less than or equal to the absolute value of 1 over x squared, which shows you that this is order 1 over x squared. All right. Ooh, look at this one. Which one will win? This one, we've got a 1 over x squared minus a 1 over x squared, right? So what's going to happen? Oh, order 1 over x cubed. Well, that's interesting. So what happen is that each piece has an order 1 over x squared, and they cancel each other out, you see? So here's the math for that, which is also known as common denominatoring. Okay, no one says common denominatoring, but you could if you wanted. You know what I meant. Yeah, so we get to this from algebra here. And okay, if x is greater than or equal to 1, then of course I can trade my denominator for just x to the 4th, right? That makes a larger fraction because I'm making the denominator smaller than it was. And then once we just have a single term in the denominator, then we can do, this is, 2 over x cubed plus 1 over x to the 4th, right? But anyway, the larger point here is that I can, of course, make the numerator larger by replacing 1 by x. And at that point, we've got 3 over x cubed, which shows you that the function is bounded above by a constant times 1 over x cubed, which means it's order 1 over x cubed. There is also big O notation as x goes to 0. I think this is of less interest to computer science probably. But you could talk about the big O notation with respect to other limits, like the limit as x goes to 0. It would mean that f of x is less than or equal to m times g of x for all x sufficiently close to 0. So it's kind of a mirror of the other idea. We're not finding something. Oh, wait, yes, we are. It's still something bigger. I'm an idiot. So here I'm looking at e to the x minus 1 minus x, right? Now, if you have a good intuition for this, you should look at this and go, oh, that's just x squared over 2 plus stuff, right? If you're thinking that way, you're thinking how you should from Calculus 2. Calculus 2, you learn series and sequences. You should use those. E to the x is 1 plus x plus 1 half x squared plus 1/6 x cubed plus dot, 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 right? So what we're doing here is we're just subtracting off the linear part of the Maclaurin expansion of the exponential. All that's left is x squared over 2 plus higher order terms. So it's totally unsurprising that we have f of x as order x squared here. And indeed, my argument is here's the Maclaurin series for x. For e to the x, we subtract off that, we get that. And then if x is less than 1, then we can replace these x's with power, with a half, and then a third. But this is not exactly e. If I add 1 to that, it becomes e. So that's e minus 1. Again, using the Maclaurin expansion. Oh, maybe e minus 2. Oh, I forgot the first two terms. It's missing the first two terms. Right? This is missing the first two terms in the Maclaurin expansion for the exponential evaluated at 1. It's like 1 plus 1 plus 1 half plus 1 over 3 factorial plus da da da. That's e. So this is e minus 2 if you look at the Maclaurin expansion for the exponential again. And so there you go. That proves that the order, big O order of e to the x minus 1 minus x is in fact order x squared. And then here's a lightning round of other ones. You can use this notation to summarize like truncated power series expansions, right? Like cosine x is 1 minus x squared over 2 plus order 4. Stuff that's higher, order 4 or higher, basically. Order 12th is the next thing that comes up here. Order x to the 4th is the next this geometric series. Next thing here, this is just the same thing, but to illustrate, if you keep going out, you could do this. And so it's a way of saying, okay, those are the terms which are negligible in comparison to everything else there in that way. So anyway, I hope that's enough for you guys to make sense of the homework. I think it should be. And then what else happens Thursday? Anything else? I think I said I'm moving the quiz up to Thursday, right? In the announcement, didn't I say that?
Yeah.
Yeah. Reason being, that way I can get it back to you guys next Tuesday before the final. It means more if you guys get feedback on that one, so